final talk of the morning, quite a humble title. If this program is achieved for me, the end of mathematics, physics, philosophy, and logic, so I'm asking you to pay attention to this talk. I'm very happy to welcome Joris from Hoeven from CNRS, Technique, and who is going to show us the path towards unification of
unification of infinities.
Yep.
Okay. Thank you, Maya. Thank you, Jean-Philippe. Thanks also to all the other organizers of this special semester, despite all the COVID difficulties. I'm very happy that everything went through. Yeah, so today I'm going to talk about two types of infinities. So actually in this talk you will get worth for your money, because there will be Transseries, but there will be even hyperseries. Yeah, so I will start with the first three parts, which are more or less an introduction, and then the later three parts, which are yeah, what is new in this program. So the first part is about one type of infinities, which are the growth rates of functions, univariate functions, germs of univariate functions at infinity. So this subject can be traced, started to become studied by Dubois-Reymond in a quite systematic way, who developed his calculus of infinities. And since, well, it was a completely new subject at that time, things were not extremely precise in his work, and this kind of things were made more precise afterwards by Hausdorff and Hardy. So Hardy in particular introduced the logarithmical exponential functions, or x-block functions, which one can see as finite Transseries in a sense. Then yeah, Hardy fields grew out as a topic, and then Transseries forms more or less a far-reaching generalization of all this, which were produced by Daan Geuring and Ekal. So, well, I think all of you have seen a lot of these things during this semester, so I will not dwell too much on all this. But about regular growth, what can we mean actually by regular growth? So there are two things basically that we can mean by this. So if we take things in an analytic way, it typically is we're going to be interested in germs at infinity, and these germs have to have some kind of regularity. So the easiest thing that one can imagine is just taking continuous functions. So this was actually a setting by Hausdorff, and one could take a subfield of the ring of all such germs at infinity, and this is called the Hausdorff field. So this is a very weak type of regularity. If we also assume that these things are the germs are differentiable, then one gets Hardy fields, so closed under differentiation for the differentiable germs. And even more regular would be if you take an O minimal structure and then take the definable germs at infinity in this O minimal structure. So this is, yeah, more or less all the types of regularity that you can expect when working with in an analytic setting. And of course, yeah, in the last setting, we not only have that the thing is closed under differentiation, but also closed under composition. Another take on germs at infinity is to go to a purely formal setting, and instead of saying, oh, I want to be closed under differentiation, I want to be closed under composition and closed under all kinds of nice things that I think are regular, is to say, I'm going to start with a few primitives which I declare to be regular, like, for instance, exponential function, the logarithm, sums, products. And we're going just to take the biggest thing that we can construct with all of this. Okay, that certainly also has to be regular. So this is, yeah, so if you do just this with infinite summation exp and log, and starting with an infinitely large variable that represents the identity function at infinity, then you get the Transseries. Okay, so this is the setting that I'm going to be interested in this talk. And so yeah, just for what is going to come, a very quick reminder about Transseries. So these are this kind of infinite expressions where you have exponentials, where you have logarithms, and you can take series, but not only series here, but also series in the exponential and so on. And the things that I'm going to use quite a lot are the Transseries can always be written as generalized series. So there are here in orange, you see coefficients, which are always real numbers. And in green, you see so-called transmonomials, which are the generalization of just powers of x. And every time, so we can write this as follows, that the field of Transseries is a generalized field of power series coefficients in R and monomials in this big M here, this Gothic M. And one very important property is that these monomials are always taken to be in a special way. They're always exponentials of other Transseries, and not arbitrary Transseries, but Transseries with infinitely large support. So if you look, for instance, the first transmonomial that we see here, it's an exponential of something that we see here, and all the terms that we have in this exponential here, so the ex of 2 and so, they're all infinitely large. They all tend to infinity at infinity. So this is really the characteristic, thing that defines the monomial, so to say, or characterizes the monomials for Transseries. Now, it turns out, of course, if this concept, which I said, regular growth, is a bit vague. And what one could want is something, a more precise definition, or at least some kind of universal context that somehow contains all regular growth. That is what one would like to have. And Hardy, in his book about orders of infinity, pointed out that, well, the class of x-block functions for him was large enough to cover, well, any kind of asymptotics that one would reasonably encounter in analysis, in number theory, in all areas where Hardy basically has done important work. Nonetheless, one can ask, are there things that obviously are not going to fit into this context? What are the holes in if we really want something universal? So one thing that Hardy asked is, can, for instance, something simple like an explicit expression, like the functional inverse of log x times log x, be expanded within this framework of x block functions? And it turned out that no. So this is something that independently was done by Lau, McIntyre, Marker, and me during my PhD. So that is an obvious kind of thing that is not covered by usual x block functions, but it is covered by Transseries. So in the Transseries, you can expand this functional inverse. Another kind of thing that obviously is not covered by Transseries is something that grows faster than any iterated exponential. So here one can again ask about regularity, and if you take a look at this functional equation here, if there is a solution to this functional equation, then definitely this solution is going to grow faster than any iterated exponential. And one can wonder, how regular can we make solutions of this functional equation? So Dubois-Reymond already constructed the first solution to this, and the nicest solution was constructed by Kneser, who showed that there actually exists a real analytic solution to this equation. So this was then also taken up later by Ekal, who constructed in his book, he not only considered this equation, but also this is called an iterator of the exponential. But if we, instead of the exponential, I put the E omega inside here, then one can get second iterates and so on, so larger, all the time faster growing things. And yeah, Ekal constructed something that he calls the Grand Cantor, which is something that is going to be closed under pure composition equations of these types. Another kind of, so he writes in his book that this Grand Cantor is basically realizing all dreams of Hardy, that of some kind of universal framework of asymptotics that you cannot not get outside of. But that's not actually quite true. So another type of problem is the following functional equation. And if you just plug in this equation f of x, you replace it in the right-hand side, then you get something like this, and you see some asymptotics that goes like this in a diagonal direction in the exponentials, and one can see that, yeah, one would need a Transseries of an infinite kind of diagonal series like this, called the nested Transseries. And this is not an ordinary Transseries. So this is also a kind of, if you wanted to solve this kind of functional equations nicely, this is the kind of other object that is lacking in the Transseries, in the ordinary Transseries. Okay, so all these are missing, so to say, missing growth rates. So if we want to construct something truly universal, then we would have to put these in. We need something where all these things are also.
This one is in the Grand Cantor?
This one is not in the Grand Cantor. Ekal, yeah, actually believe that this, at a certain point, that this can be expressed in terms of this one, but that is not true. Okay, other types of infinities are the numbers. So Cantor, who was contemporary to Dubois-Reymond and actually struggled quite a lot with him, introduced another type of calculus with infinite numbers, which is the calculus with ordinal numbers, which is just counting beyond the natural numbers, and also being able to assign sizes to his newly created sets in his set theory. Another kind of thing that one may want to do with numbers is things like non-standard analysis. So you have real numbers, for instance, and you would like to add infinitesimal numbers to that and to be able to compute consistently with that. And yeah, the ultimate extension of this line of thought was introduced by Conway with the surreal numbers. You probably also saw a lot of talks already about this. I will very briefly review what I am going to need. So surreal numbers have a very nice inductive definition. So the surreals together with the ordering on the surreals are simply the everything that you can get with the so-called Conway brackets. So if you have already constructed a set of surreal numbers L and there's another set of surreal numbers R such that every member of L is inferior to any member of R, then this Conway bracket basically just constructs something in between. And that's all. All numbers are constructed in this way. So this is a kind of ultimate generalization of Dedekind cuts. Now, this definition is not so easy to compute with directly. So another kind of more explicit definition, and not a recursive one, but completely explicit, is using sign sequences. So just take any ordinal number and take a sequence of signs of this length. And that's also a surreal number. And we can simply order such sequences in the lexicographic way by also using the convention that if we are comparing two sequences of different length, we just complete with zeros, and minus is smaller than zero, and is smaller, which is smaller than plus. So that is another kind of thing. And with the sign sequence definition, there is another relation that one can define, which is the so-called simplicity relation, which simply states that a number is simpler than another number if its sign sequence is a prefix of the sign sequence of the second number. So plus plus will be simpler than plus plus minus plus, for instance. And basically the simplicity relation turns out to be equivalent in a sense to the Conway bracket. So both can be defined in terms of the other one. For instance, the Conway bracket can simply be understood as being the simplest number that lies in between L and R, using this simplicity relation. Now, the nice thing of the surreal number, the magic of the surreal numbers, is that using these recursive definitions using the Conway bracket, one can one can define all kinds of operations, for instance, the ring operations. So 0 will simply be the simplest number between the two empty sets. So it's basically the simplest number that there exists. 1 is the simplest number which is bigger than 0. And here we see definitions of the ring operations. And basically, we just state the natural the properties that have to be satisfied to make these ring operations compatible with the ordering. And if you state these properties, then it turns out that these definitions actually define a ring structure on the serial number, so that the ring axioms are satisfied. And in fact, it's even a real closed field under these definitions. Gonchor later on also showed how to define an exponential function on the serial numbers. This definition is a bit more complicated than the ones here, but it's in a similar spirit. And it turns out that the first order, that this thing is elementary equivalent to the reals with the exponential function. So it satisfies all the same properties as the usual real numbers, but now for surreals. Another interesting map is a generalization of Cantor's omega map on ordinal numbers. And so omega power something. Omega is here the simplest infinite surreal number. And also the first non-finite ordinal. And using this bracket notation, one can define, extend Cantor's ordinal exponentiation to the surreals. And this is interesting because basically, if we define the images under this omega map to be so-called monomials, then Conway showed that any surreal number can actually be written as a generalized Hahn series with real coefficients and monomials over these monomials. So yeah, well, you probably have seen lots of examples already during this semester. So here you can see that how to get all kinds of real numbers. So all the real numbers are in particular surreal ones. If you take on the right-hand side always the empty set, one reproduce all the ordinal numbers. And since things are closed under division and exponentials, you can also have surreal numbers like 1 over omega or exp of omega and so on. But there's also some missing structure. So for instance, is it possible to differentiate a surreal number with respect to omega? Would it be possible to make sense of such a thing? So in fact, this was done by Berarducci and Mantova, who constructed a derivation with nice properties with respect to exp, log, and infinite summation. And actually, it turns out that the surreal numbers under this derivation satisfy the same theory as the Transseries. So it's a so-called H-closed H-field. So it satisfies nice properties. Still, as we will see maybe a bit later, I don't think it's the really right derivation on the surreal numbers that we are after, because it will not be compatible with the hyper exponentials. So these things like E omega that satisfy that functional equation that I showed on the previous slide. And yeah, one can also ask, is it possible to compose? So this is the kind of questions that one may want to answer on surreal numbers. Okay, so now we have two types of infinities. A priori, these are completely unrelated. They come from different origins. One talks about numbers, the other talks about germs at infinity of functions, not at all the same a priori. But there are also a lot of similarities. Transseries can be seen as an extension of the real numbers with an infinite element x. There can be considered as generalized series. We have an exponential and a logarithm that are defined on it. And surreal numbers, something similar holds. We have now the infinite elements called omega, and they're series, and we also have exponentials and logarithms. But there are also differences, right? Because here, transseries are functions. So we can differentiate, we can compose. Whereas surreal numbers have this curious, this somewhat exotic structure of the Conway bracket and this simplicity relation. So because of these similarities, it looks nevertheless like these things actually should be the same kind of thing. So that's why, in my book about transseries, I made this conjecture, which one could call the infinities conjecture, that if we take a suitable generalization of the transseries, which we will from now on call hyperseries, the field of hyperseries nx, infinitely large variable, should be naturally isomorphic to the surreal numbers. And the isomorphism should be very simple. It consists just of replacing x by omega, evaluating the thing at omega. So because of the lacking kind of functions in transseries, of course, in H, we need it to be closed also under all the hyper-exponentials, so these iterators of the exponential, like the e omega that we already saw. They're functional inverses, which are called the hyperlogarithms. And it should also contain all these kinds of nested hyperseries that we saw that went up diagonally. Now, if such a conjecture is true, then this is nice because it means that we can transport structure in both ways. So it would mean that on the transseries, for instance, we would have a Conway bracket. Okay, well, not on the transseries, actually on the hyperseries then, right? But we would have a simplicity relation and a Conway bracket. And on the surreal numbers, for free, we would get a differentiation and a composition, basically. Yeah. So we would be able to take Conway brackets of sets of hyperseries and get new hyperseries. Okay, so so this is really the program. So this kind of this program actually started a bit before this conjecture, because when I was doing my PhD, I was not aware of the existence of surreal numbers. So basically, one could ask already without knowing of surreal numbers, can we construct some sufficiently large space of hyperseries that in which we would be able to do all kinds of formal asymptotics with regular growth rates at infinity. And this is actually what École claimed with the Grand Cantor in a sense. But as we saw, for the nested kind of things, the Grand Cantor is not sufficient. So yeah, so some early work I did in my PhD. I actually constructed the first class-sized field of Transseries with that is closed under differentiation, composition, and infinite summation. So this is much bigger than the usual field of Transseries that you may have seen, which is typically one restricts the kind of logarithmic depth and exponential depth that Transseries can have. So a series like x plus log x plus log log x plus log 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 x typically is not allowed, but it is allowed in this field. Okay. Then yeah, I also discovered the existence of these nested kind of Transseries, but we still needed a theory where this could fit in, where this could be described precisely. So there is, so this required to develop a so-called strong linear algebra, which is a generalization of linear algebra with this kind of big summation symbol on generalized power series, and generalized fields of Transseries in which we could have nested Transseries or hyper exponentials and things like that. And a big part of these things were first published in the PhD by my former student Michael Schmeli, who went into the private sector after his PhD. So there we constructed. They were still called Transseries, but Transseries where we also had the hyper exponential closure under hyper exponential hyperlogarithms, but only for finite number of iterates. And then, yeah, after that, somehow, for a long time, I did other things. It didn't seem at the time that it interested a lot of people also. So that was another reason. And then at a certain point, Berarducci and Pantova came up with their construction of their derivation. So yeah, this we retook up this whole program actually slightly before that they published this thing. And there is a big series of papers that came out of it. So first of all, we had to construct, of course, formally construct these fields of hyperseries. So for this, together with Lau and Elliott, we first constructed the field of logarithmic hyperseries. So no. And then together with my PhD student, Vincent, Bagayoko, who will defend this autumn, we, on the one hand, we constructed formally also with Elliott these hyperserial fields, and also the counterparts on the surreals. I will talk a bit about surreal substructures in a minute. Then show define hyper-exponentials and hyperlogarithms on the surreals and show that it indeed has the nice structure that we want. And at the end, prove that any surreal number can actually be written as a hyperseries in omega. Okay, so right. Okay, so let's see a bit how this works. So first we need logarithmic hyperseries. So basically, alpha here is going to be an ordinal, any ordinal number, and we're just going to define this formally. So we're having a symbol L of alpha, so a hyperlogarithm iterated alpha, or a logarithm iterated alpha times. And applied to x, we just call this L of alpha here. And the monomial group that we can make out of this is just take all real power products of these things. So in a sense, one can see this as being a monomial being characterized by a sequence of real numbers of ordinal length, a bit like the surreals where pluses and minuses, but now instead of pluses and minuses, we have just general real numbers. And again, this has to be ordered. So we again take just lexicographical ordering on this, and this defines naturally an asymptotic if we consider this as exponents of these hyperlogarithms. It defines an asymptotic big O, small o kind of ordering on the this formal group L of monomials. So that's it, and we just take all series, Hahn series with monomials in that group, and those are the logarithmic hyperseries. So the semantics of this is that the Ln for finite n are just the iterated logarithms, and that if we have an arbitrary ordinal and we write it, its standard the Cantor normal form of this ordinal, so that is a finite sum of omega power things times integers like this, then basically the L of this is just the composition of the corresponding L things, but the other way around. So for instance, the omega square plus 1th iterate of the logarithm is just the logarithm of the omega squared iterate of the logarithm, and the L of omega power mu satisfy these kinds of functional equations that we saw already before. So if we go from mu to mu plus 1, then the composition of these two is just it conjugates the former one with the shift map with respect to shift map with 1. That is a property. I mean, the definition is just this formal thing. Okay, it's a formal definition that is just all logarithmic hyperseries are like this. Then of course, what we want to do is define structure on this. Okay, and we're going to make this structure. We're going to do our definitions in such a way then of the structure on it, so a composition, a derivation, such that all these things are going to be satisfied. Okay, and this is the semantics. I talked about semantics. So this is the semantics that we want. Okay, it's not the definition of composition, but it's the semantics of composition that we want. We also have the semantics of differentiation that we want. Just taking the derivative of a hyper logarithm is just going to be the power product of 1 over all previous hyperlogarithms. So here you recognize things like if you differentiate x, you get 1. And if you differentiate log x, you get 1 over x. Then if you differentiate log x, you get 1 over x times log x, and so on. And now, for instance, if you differentiate the omega iterative logarithm, then you would get 1 over x log x log x log x, and so on. Okay, and you can go on like this. Okay, forever. So, so for instance, the L of omega power omega. Okay, omega power omega. Omega is not the successor ordinal, so it doesn't satisfy this kind of functional equation, but we can still compute the derivative of L omega power omega like this. Okay, so there's no functional equation for L omega power omega, but there is this property for the derivative. Now, basically what we do in our paper with Lau and Elliott is that we construct a strongly linear derivation on this class of all logarithmic hyperseries, as well as a composition, where we always compose with things that are both positive and infinitely large, so bigger than all real elements. And this composition is again strongly linear in the first argument, so it preserves infinite summation. Okay, and moreover, it turns out that one can do Taylor series expansion for this kind of for this composition and the derivation. Now we want to add hyperexponentials. So this is more tricky, right? Because we already have to have something that is analogous to what we had for monomials with the usual Transseries. I already mentioned in the beginning of my talk that the monomials in Transseries were characterized in a simple way, namely that the logarithm of a monomial is always an infinitely, the support only contains infinitely large transmonomials. And with this property, this makes it easy actually to define an exponential on the Transseries. Why? Well, if we want to take the exponential of some big Transseries, like the one that we see here, we cut the Transseries in several parts. One part which consists of all the terms with monomials that are infinitely large, then a constant, and then those that are infinitely small. And basically, just using the functional equation for the exponential, we can then rewrite this exponential like this. Now, if we have something which is infinitesimal and we take the exponential of it, we can just do a Taylor series expansion of such a thing. So this thing is defined, on the right-hand side is defined for free. Here we just have the exponential of a real number, which is also for free. And by the characterization of transmonomials, the exponential of this thing is just a transmonomial. So so if we declare that these are the transmonomials, we can just formally exponentiate the green part here, and this defines the exponential on all Transseries. So we would like to do something similar in the case of hyperexponentials. But then the question is, where? So here it was clear where to cut things. So this Transseries here, we cut it precisely at the parts where, at the constant term here, and the monomials are the ones, the exponentials of the things that are before here. So basically, in order to understand what we have to do for hyperexponentials, we need to find the place where to cut our things. So for this, the question is, if we take a hyperexponential of something like this, like x plus 1 over x, for instance, what happens if we want to expand this as a Taylor series? So the point here is that this hyperexponential of x is very large, right? It's really a very fast growing function. So basically that means that the derivative is even much bigger. So if we look at it here, more precisely, it is as follows. It's the product of hyperexponential of x and the hyperexponential of x minus 1, which is also the log of the hyperexponential of x, and so on. So if we just put the 1 over x here, this is way too weak to make this thing converge. Okay, so this thing, yeah, we cannot expand this as a Taylor series. Basically, this thing should already be a monomial, and even something which is stronger than a monomial, something like a hypermonomial or something like that, right? But now if we put 1 over e omega of x here, okay, so now this is going to cancel against that one, and then here we have just the log of e omega x, which is much smaller than what we have there. Then we have something that does converge. Okay, so if the thing here in blue is sufficiently small, then we still can do Taylor series expansions. And the question is a bit, where very precisely do we need to cut? So what about 1 over the log of this thing? Now if we do that, then we see that it just cancels out the thing that is here against this one. And what we have here is still very large, right? With respect to that one, because it's multiplied basically by e omega of x minus 2. So this does not converge. Okay, so we might be tempted to say, okay, this thing is going to be some kind of hyper monomial, but this is forgetting something, that we could use the functional equation. So if instead of x, I put x minus 1 here, then for the reason that I just told, we get the same situation as with x in the previous slide. And this one does converge, basically. But if we replace x by x minus 1, due to the functional equation, we can rewrite this as the original one, as the exponential of this one. So basically, what happens here is that if we assume that we already had something that is closed under exponentiation, and then in order to define this hyper exponential here, we actually only needed the hyper exponential of x itself to be defined, because then with all these functional equations, we can just rewrite things in terms of that. So yeah, so that gives a precise then location of where we can cut these expansions for things to be expandable, and so the kind of really essentially new hyper exponentials that we have to add are going to be things of this form, which have this very, a bit technical property on the supports. that was illustrated by what I just showed. And another way to see it, it turns out that this is equivalent to saying that not only the elements of this m omega are monomials, but any finitely iterated logarithm of this monomial is again a monomial. So we call this log atomic elements. So these are monomials, and the log of them is again a monomial, and log of it is a monomial, and so on. Okay, and these are precisely the kind of new hyper-exponentials that we need. So these are going to play a similar role as monomials in the setting of Transseries. And for instance, if you took the x plus 1 over x thing, then basically the hyper-exponential of this thing is precisely of this kind. So all the things that I wrote here, so the logarithm of this thing, which is just obtained by replacing this x by x minus 1, and then the log of log, I cannot correct. Yeah, there is a 2, it should be a 2 here, and so on. All these things are basically log atomic monomials, and in particular monomials. So basically, if we are able to construct fields of hyperseries with a hyperlogarithm just for the log atomic elements, then we can, just using Taylor series expansions, extend it to everything. Okay, so this gives a bit the flavor of hyperserial fields. So the kind of properties that we want is that we have a field of generalized series. We can compose with, on the left, with any logarithmic hyperseries. So this is very useful to have directly to be able to compose with any logarithmic hyperseries, because it means that we can essentially write these kinds of Taylor series expansions that you just saw. And then we have this a bit technical property on the supports of hypermonomials, or the log, the omega power mu log atomic elements. Then there are other properties. So basically what we showed is that we can, if we start with such a hyperserial field, we can close it off under all hyper-exponentials. Okay, so now the surreals. The property that we're going to use on the surreals is that what is very special about the surreals is that we have this simplicity relation. Now, if we forget about everything else on the surreals, it is actually interesting to just look at the surreals together with the ordering and the simplicity relation, and see if there are any other things that are isomorphic to this, because this particular structure, in fact, appears over and over again everywhere inside the surreals. So we say that some subclass of the surreals is a surreal substructure if, with the restricted relation is basically isomorphic. So there are lots of examples. So for instance, the positive, strictly positive numbers, the positive infinitely large numbers, but also, for instance, all monomials. All these things are surreal substructures. And since this isomorphism preserves simplicity, it should also preserve the Conway bracket. And if it preserves the Conway bracket, it also gives a way to define this isomorphism just by induction. It preserves the Conway bracket. So that gives a recursive definition of the isomorphism between the surreals and any surreal substructure. And this gives all kinds of interesting functional relations just because there is a unique such isomorphism that is given like that. And for instance, for the positive surreal numbers, this thing is just obtained by looking at the sign sequence and putting a plus in front of it, just one plus. So then what we obtain, it will also always be positive. And this is the kind of thing that preserves the Conway bracket. Infinitely large positive, we do not put just one plus, but omega pluses in front of it. And for the monomials, it's just the omega map. Now, an even more systematic way to obtain.
So you have 2 minutes.
Ah, okay.
Try not to be too systematic.
To have the is so we have a group action on the surreals, and then for instance, let's say multiplying a surreal number, a positive surreal number by a positive constant, real constant that defines a group action. And we can look at the convex hulls of orbits under this action. And one of the theorems that we prove is that these convex hulls under natural conditions form always a surreal substructure. And this allows us to define several interesting subsets. For instance, the log atomic elements in the surreals, we can obtain them with this group action where we replace x by the thing that you see here. So we pre and post compose with exponent iterated logs. So in particular, this means that all these log atomic elements form a surreal substructure. Similarly, if we look at these nested things that we had here, there is a natural group action on it. And here again, these elements will form a surreal substructure. Okay, so I'm maybe going to skip some of these things then. So this allows us then to using the properties that I said about these cuts and where we have to declare, when we have to declare that something is a hyper exponential, hyper monomial or not, and then using one can define these things. Okay, so well, let me state the results. Okay, so we obtain we can define the hyper exponentials and the hyper logarithms so that it gets this structure of a hyperserial field. And actually we can do a bit more, and that is to show, let me say, show this one to finish. There are certain, one can look at the set of all expressions like this that make sense. So formed using from omega, using hyper exponentials, hyper logarithms, infinite summation, and so on. So here I have shown one, and in these expressions, I'm also allowed to have these things that go up in diagonal. But as we saw, the nested numbers actually forms serial substructures. So they're not, if you just write an expression like that, it doesn't correspond to a unique number. There's a whole class of numbers that you can get in that way. And basically what one has to do in order to really describe which number you get is to, inside an expression like this, you look at all these infinite diagonal parts inside. There can be several of them. And for each of these paths, if you truncate everything that is beyond, you get a so-called nested number. And the nested numbers of this type will all be parameterized by a unique serial number. So if to any path, red path here, we associate a serial number and see this as part of our expression, okay, this is going to determine a unique serial number. And so, and then the end theorem is that any serial number can be written in this way. So one really doesn't miss anything. Okay, so this is the kind of thing that you don't have as a usual Transseries, right? Because if you take something like the hyper exponential of omega, for instance, you don't see how to write it just with exponentials. Well, you can take logarithms of it, and you will see that the logarithm of it is again a monomial, and so on. But it never ends. So there is just a small a subclass of things that you can write as Transseries. But here you get all serial numbers. So this makes us confident that you really get everything, right? Because this means that you also have a Conway bracket on the hyperseries. So if you take any cut in the hyperseries, then what we already know something that we can put in between. Okay, so if there would be something that we couldn't cover in our thing, yeah, where would it fit in, right? You don't see where to put it anymore. So yeah, so thanks.
Thank you.
Stop here.
Slightly out of time, but okay. Questions? Mathematics.
Is there about your condition in hyperserial field, the one on the support, is there an analytic interpretation? I mean the one HF3.
Yeah. Well, supports don't have really any interpretation, right? Already just in normal Transseries, this characterization of transmonomials doesn't really have any analytic interpretation. The interpretation might be where the cut occurs, basically. And when there is a cut that occurs, there is underlying to this, there is a group action of transformations that preserve this cut. So for instance, if we take just the normal Transseries, okay, the normal Transseries, and you take all shifts by a real number, okay, this is a group action on the normal Transseries. And under this shift, if you take the convex hull under this shift action, for any Transseries, this convex hull will contain an element with support that of only only infinitely large elements. So that could answer what the analytic meaning of this is, right? That there is a group action that corresponds to this cut.
Another question, a comment?
And the whole program, just wondering, you listed the various papers you said that I was just wondering, has the last step been carried out already? Or?
Oh yeah. This one. Yeah, I submitted it to Hull, the preprint archive. So I think it should have already appeared, but probably this week it will be at a certain point it will appear.
Does that mean that the composition on you have
here we have just constructed the hyperserial fields, right? So we don't claim here that we have a full composition or full derivation on these hyperserial fields. So this is work in progress to show that if we have a derivation on this big H and the composition, then it will automatically give this also on the surreals. But we still have to show this is work in progress. So yeah, Vincent was more or less done with it, but I think there are still some simplifications maybe here and there. So we're working on this.
Good question.
And this will prove your conjecture.
Well, the conjecture, in a sense, is proven, right? More or less. Well, I say more or less because we don't really construct this field H. We get it somehow as a side product of the theorem that I state. We could declare that H is simply the thing of all the expressions that you have here, and it has the structure of a hyperserial field. We could just declare this is the hyperserial field of everything in omega. Okay, but yeah, it's a bit cheating, right? It would be nice also to have a more inductive construction of H itself, from not relying on surreal numbers.
Okay, thank you very much.
Okay.
So, thanks.